Hit record. All right. Before we really get started here, I want to kind of talk about some differences in symbols that right now the distinction isn't crazy important, but it's something that I want to start introducing to you. Okay? Now, so far, we have used the symbol X bar to represent the mean and S to represent the standard deviation. Okay, those are values that we use to describe a sample of things. Okay, when we say sample, like you guys are a sample of Grandview Heights students. You are not all Grandview Heights students. Cool? Right? And so when we talk about populations, which is kind of what we're going to be talking about today, okay, when we're talking about a population, the symbol for a mean is slightly different. We use something, the Greek letter M. It's pronounced mu, M-U, and it really is just a curly Q M like this. Okay, that is the mean of a population. The standard deviation of this population is the Greek lowercase sigma. You don't need to know uppercase versus lowercase. And in fact, if you don't call it sigma, if you just call it that, 0 with a line on it, I'll still know what you're talking about. But don't do that on the AP exam. Just actually draw the symbol, okay? Because they won't know 0 with a line on it. So when we talk about a population mean, we use the symbol mu, and when we're talking about a sample mean, we use the symbol X bar. Right now, it's not that big a deal. In like a month or two, using the wrong symbol will be a big deal. So I'm pointing it now. Let's say you're taking a quiz on Friday, because you're taking a quiz on Friday, okay? Let's say on Friday's quiz, you use X bar when you're supposed to use mu. I'm still going to correct it, like I'll write you a little note, but I'm not going to take any points off for it yet. I'm going to be using the proper symbols. And they're not necessarily interchangeable. They just mean because they mean two different things, the mean of two different groups, but they're similar in nature. All right. So the big idea today is the normal distributions. And we are going to use normal distributions all year long. They are actually one of the more important pieces of statistics. Yeah.
Wait, so are we going to use X bar again? Or just
yes.
So what's the different situations for X bar and mu?
Whether or not your data is coming from a sample versus your data comes from a population.
Is population mu?
Mm-hmm. Okay. So, a normal curve is anything, for right now, anything that you guys see is bell-shaped. We're going to call approximately normal. And in order for something to be bell-shaped, I know this sounds silly, it needs to have a tail, a cap, and then another tail. And they are, in fact, approximately symmetric. Okay? Everybody good so far? Can I draw you two examples of things that are not normally distributed? Okay? If you draw a normal curve that looks like that, I'm going to have a problem because that is not a curve. Cool? And if you draw one that looks like that, I'm going to have a problem with it because that's not bell-shaped. But if your normal curve, you don't have to be perfect. If yours looks like that, that's fine. Okay? My normal curves, I've been drawing them all day, every day for 8 years, so mine tend to be a little bit smoother. Yours don't have to be perfect. I need to tell that they are bell-shaped, curved, and tails. Is everybody okay? And it turns out that in a normal distribution, I could give you a histogram that's approximately bell-shaped, right? Okay? We can estimate the standard deviation by looking for where is that switch from when it's like those tails that curve up and the cap that kind of opens down. Okay? The mean goes smack dab down the center. That distance between where that difference between opening down and opening up is, that's where my, that distance is one standard deviation. Okay? All right, now, if I were to describe, let's go ahead and if I said the distribution, and this is actually true, of IQs are normally distributed, or I'm going to say approximately normal, with a mean of 100 and a standard deviation of 15. Would that be a good description of the distribution? In other words, remember those good descriptions describe shape, center, and spread. Have we described the shape? How did I describe the shape? When I said it's normal, that tells me bell-shaped. That communicates a lot. Have I described the center? With the, what's the center? The mean, so fit the centered at about 100. Have I described the spread? With the standard deviation. So to describe a normal distribution, we typically use the mean and the standard deviation as the measures of center and the measures of spread. How are we feeling so far? All right, now, normal distributions tend to follow what we call the empirical rule, sometimes called the 68, 95, 99.7 rule. It really rolls off the tongue. Basic premise. In a normal distribution, I plot my mean, wherever that is, okay? If I go one standard deviation away on each side of my mean, that contains 68% of the values. In other words, the relative frequency for the group that's here, one standard deviation on each side, that relative frequency, 68%. Okay? If I go two standard deviations away, I now have 95% of the values. So, you guys remember that whole two standard deviations away is considered to be an outlier? Start thinking about what percent of the values are in here if this is 95%. 2.5 on each side. So in order to be more than two standard deviations above the mean, you'd have to be in the highest 2.5%. Or to be more than two standard deviations below the mean, you'd have to be in the lowest 2.5%. Okay? That's why it's not low. Like that's pretty extreme. If I go one more standard deviation on each side, that's 99.7% of all the possible values. Ends up being a lot. We good so far? All right. And it turns, if I do that we can actually use this in a real world setting. So imagine, have you guys ever seen like the How It's Made where they talk about cans of soda being filled? It's pretty cool. Like they have this little conveyor belt, and what they have are the cans without the tops on them. Okay? And then they have this machine that goes whoosh and in drops the soda. And then it's on a conveyor belt, right? So then it goes over, and then the machine goes whoosh, and then goes over, and then whoosh. Can you guys kind of envision what this looks like? Okay. And do you think that machine's perfect? Do you think most of the time the machine's close to perfect? Okay. And if I asked you to describe the distribution of the amount of ounces going in that soda, right? Most of the time it's going to be pretty darn close to the mean average. But sometimes it's going to be a little more, sometimes it's going to be a little less. And typically in some of those manufacturing processes, what they do, especially for sodas and stuff like that, is they slightly overfill, okay, to be on the safe side. So we're going to go ahead and say that the mean amount of soda is 12.05 ounces. And that the standard deviation of the soda, which I'm going to kind of write out here on the margin for now, is 0.07 ounces. And so one of the things I like about normal distributions is so many things are normally distributed. It's also really helpful to help us figure out like what is that reasonable amount of soda. Would you guys be super surprised to get a soda with 12.25 ounces in it? You know what I'm going to do to kind of help myself wrap my brain around that? I'm just going to go up. Let's see. One standard deviation would be 12.12, yeah? Two standard deviations would be 12.19. Three standard deviations would be 12.26. So yeah, 12.25 ounces is more than two standard deviations above the mean. It's almost three standard deviations above the mean. That's pretty unlikely. Okay? So there's one of the things I like about describing things as normal with standard deviation and stuff is we can see a lot of things. Okay? All right? And likewise, if I go on the other side, this would be 11.98. My graph here isn't as clean as I'd like it to be. And then we'd have 11.91. And then 11.84. And all I'm doing is adding that 0.07 or subtracting that 0.07. Right? And so, guys, if I asked you what percent of the points are in this section, right here, in between that, what would you say? Not 68, 34. Because it's only half, right? And then from here to here, that would be 34 as well. What about in this section? Oh boy, that's not what I wanted to do. What about right here? What area is that, do you think? Let's think it through. Thirteen and a half. Okay. So guys, this section and this section and everything in the middle is 95%, right? So if I take this 95% and I forget about this stuff because it's already there, that's 68. Okay? These two combined have to be 27%. And if I cut that in half, I know that this is 13.5%. Oh boy. As is this one. Now, those are approximations. They're not perfect. Okay? And then between these ones, this is 95%. If I add these ones in, that's 99.7%. So I just added another 4.7%, making this one 2.35%. And this one, 2.35%. What does that make the outer tails? Here and here. 0.15%. And this sounds like a silly question, but what does that make all of it? 100%? And if I wrote that 100% as a decimal, that would be 1. So what we're going to be doing a lot is we're trying to figure out what percent of values match something. We're essentially finding the area under this curve. And the total area under this curve is always 1. In your head, you can also think of that as 100%. Okay? So if I were to ask you, what percent of cans have more than 12.12 ounces in it? I'm essentially asking you to find the area to the right of 12.12. Which essentially is this plus this plus this. That's one way to get there, yeah? %. How would you guys feel if I told you then 12.12 ounces is the 84th percentile? Would that make sense to you, y'all? Because what percent's beneath it? If there's 16% above it, there's 84% beneath it. So I'm maybe trying to lay some groundwork that the area left of a place on this curve is also its percentile. Which when you think about, you guys go to the doctor, right? When I asked you where you saw percentiles, you either saw it on your standardized test scores or at the doctor's office. You know your height in percentile. Guess what we can say about heights? They are normally distributed, and the doctor's charts, like the people who created those for the doctors, they're using this exact same idea, which is kind of cool, I think. How are we feeling about normal distribution so far? All right. Okay, guys, how much between 11.98 and 12.19?
$81.5.
81.5%. All right, now. If I make a dot, like, there's a dot plot here, yes? These are all just dots? Okay. And I'm going to assign each of them an x. The x being the variable that we're interested in here, the variable being the amount of soda that's actually in a can of pop. Is everybody good? Could I calculate a z-score for each one of those values? We did z-scores yesterday, right here. What would the z-score for all of these x's be? 0. Because how many, if it's exactly the mean, its number of standard deviations from the mean is in fact 0. So what if we made a normal curve of all those z-scores? So all those ones in the middle would have a z-score of 0, so the middle of this curve would be 0. Everybody with me? All these points that are up here on this spot right here, what would their standard, or what would their z-score be? 1, because they are 1 standard deviation above the mean. So we'd have a couple here. What about here? These ones. What would they be? -1, because they're 1 standard deviation below the mean. And then we could keep going all the way out. So if we start thinking about this bell this time, if I asked you, what is the mean of this graph and what is the standard deviation of this graph of these z-scores, what would we get? The mean would be 0. The standard deviation would be 1. And folks, this is what we call the standard normal curve. It is the normal curve of standardized values. Now, oh my gosh, Leo, you're going to help me out so much. Can you look at that can for me for a second? Okay, and how many ounces does it say is in there? 12. How many milliliters?
355.
355. This can right here, if I measure it in ounces, it's here. If I measure it in milliliters, I would have a completely different mean, a completely different standard deviation, but it would still be here, right? And the z-score for that can is still right here, if that's Leo's can, because it might not have exactly 12, right? Okay, so this standardized normal curve is how we get to start comparing different things to each other. Okay, and everybody good? All right, sweet. Last question. We got, what when we went to the right of 1 standard deviation, we got about 16%. Okay? All right, so here's what you're, so anytime I ask you about a z-score, the mean of all the z-scores is always 0. the standard deviation of all the z-scores is always 1. It doesn't matter what shape the distribution, it's always true that the mean of all the z-scores equals 0 and the standard deviation of all the z-scores always equals 1. That's always true. And it turns out that these normal distributions are so prominent that your calculators have been pre-programmed with how to do a lot of things in them. So for instance, what if I asked you, what is the percentile if it's 1.2 standard deviations below the mean? That starts to feel a little bit weirder, okay? Because we can't just use that 68-95 rule. And since it's curved, we can't just be like, try to pretend like we could figure it out using lines and stuff, okay? So, calculators. Now, your calculators, let me do this, and then I'm going to actually do this and this-ish. Your calculators are pre-programmed with lots of things, one of which is a set of known distributions. Okay? Now, search calculator. Find something that might help you deal with known distributions. You guys see where it says distra right above the vars button? Okay. Go ahead and hit second vars to bring up the distribution menu. That was never the distributive property, right? It's the distributions menu. And inside this menu, your calculator has a ton of pre-known, easy to calculate distributions. Does anybody see anything that might help us with a known normal distribution? The third one, where it says inverse norm?
Oh, maybe not.
That is one of the ones we're going to use. Anything else? Two? Anything else? One looks like it's going to be helpful to us. It's actually not that great an option. We're always going to choose either 2 or 3 in this menu. And it depends on what we're going to do. I'm going to start with the one that says normal CDF. That CDF stands for cumulative distribution function. And so let's go ahead and say, before we just did 1 standard deviation or higher. Let's go ahead and look at what that might look like when I choose normal CDF. So go ahead and choose option number 2. And my guess is it looks something kind of like this. It asks you for a lower, an upper, and then it has this symbol that is intended to be kind of like that curly Q mu, and then standard deviation. Okay, does yours have that? Jaden, does yours have that?
Yeah.
Okay. Anybody else have a black and white calculator? Does yours have it? Yours has it. Okay. All right. Now, the lower and the upper is asking you to describe where is it shaded. What part of the graph are we trying to find? When we're looking here, what's the lower boundary of where it's shaded? 1. So for your lower, go ahead and put 1. For your upper boundary, is it shaded? Did I stop shading at 2?
Oh, no.
Did I stop shading at 3?
1 trillion.
Did I really stop shading? If I'm just trying to do bigger than 1? Leo, it's no fair. I'm actually shading forever to the right, yes? But you can't put infinity in the calculator. So you're just going to put in, a lot. I was going to say a gajillion. Just put a really big number there. Okay? I can't. Now, what should we expect this answer to be? We said here, like yesterday. do, go all the way down to hit paste, and when you hit paste, it'll, oh boy. Leaving this slide was a bad idea. Nope, 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 nope. And when you hit paste, it'll show you this formula with it all filled in. Go ahead and hit enter. And we got 0.158. Are we good with that being the approximation being 16%?
Yeah.
Everybody good? Okay. And what would we expect for if we did between -1 and +1? What would we expect that answer to be? 68? Maybe? 68%? Because that would be within that 68, 95, 99.7 rule. Okay, so I go to normal CDF. I go from -1 to +1 this time. Because my left-hand boundary of shaded is the -1. My right-hand boundary is this making sense? So the lower and upper describe where have I shaded my graph. Okay? And then the mean and the standard deviation for right now, we're just going to keep as 0 and 1. I hit enter. And I get 68%. About what we'd expect. All right. Now, so what if I said, what would it look like less than 1.2? So if I draw that picture, my mean 0, my standard deviation is 1, I'm at 1.2, and I'm just going to shade to the left because that's where we're less than. So I go to my second vars, choose normal CDF, which I put for my lower in this case. Negative a gajillion. My upper should be 1.2. I've got my 0, I've got my 1, and I find it to be 0.885. Oh, it's 0.885. Yeah? Is this feeling good? All right. What if I said more than 1.3? I'm sorry, more than -1.3. What are we getting? 0.90. Does it make sense? Do these two answers, when you look at these two answers next to each other, can we see that there's a little bit of a relationship there? Like, if this had been -1.2, like right here, these two graphs would be mirror images of each other, yeah? So this is just a little bit further, so it's adding just a little bit more. Is this okay? All right. Hold on. So what if instead we come down here and I say, I don't know the z-score, but what I know is that I want to find the value for that z-score so that this area is 0.61. What do you think? I mean, essentially, we're asking the calculator to work backwards. And in the math world, working backwards means using the inverse operation. Okay? So go ahead and hit second bars again, and this time you're going to bring up, I hit the wrong thing. The option number 3, inverse norm. And when you ask it for the inverse norm, it asks you for an area. Yours probably looks a little different. Yours probably doesn't have the left, center, right. It doesn't, and yours probably doesn't have the left, center, right. Okay. You guys will always be dealing in left. Your calculator just automatically does the left. Okay. So the area we're going to give it in this case is 0.61 because that's the area I have shaded. And those of you that have that left, center, right, which area do we have shaded right now? So we want to make sure the left is highlighted. And we go down, we hit paste. Now, before I hit enter, don't hit enter. What do you guys think this answer should be? Is it going to be positive or negative? Positive is going to be really big, or it's going to be positive but close to 0. Are we comfortable with that idea? And the reason I say this is we're about to get lots and lots and lots of decimal answers. Making that prediction in your head of what you think it's going to be can really help avoid like second guessing yourself. Does that make sense? Does it make sense that we get z equals 0.279? Slightly positive? Just above 0? So, if we know the area, we use inverse norm. If we know the boundaries, we use normal CDF. What happens if you get them confused? The calculator is going to ask you for something you don't know. And when the calculator asks you for something you don't know, what do? Go back and go to the other one. Now, it is in your best interest to have kind of a cleared out nothing on your screen when you hit that bars menu. There's some times where you can really go down a rabbit hole of inserting wrong things in the wrong places. Okay. So, let's use your calculator. Ta-da. If I ask you to find the z-score for the 33rd percentile of a normal distribution. Well, anytime I ask you to do anything in a normal distribution, the first thing I might do is draw a picture of it. Okay? And if it's a z-score, the z-scores always have a mean of 0 and a standard deviation of 1. And what does it mean for something to be a 33rd percentile?
The 67%. So the middle part.
Not per percentile. You're thinking 68% of those middle, but for percentile is the very specific definition of the percent is that value or lower. Okay? So if something is the 33rd percentile, I don't know what it is. I'm going to put a Z right here because I don't know what it is. But I do know that the area smaller than it is 0.33. And what kind of answer should we be getting here? Positive or negative? Negative, because it should be below the mean. Yes? Okay? Remember that z-score is the number of standard deviations above or below the mean. It's still where we are. And what are we getting? 0.44, negative 0.044. Which calculator function do I put in here? This is inverse norm because we know the area. What's up? All right. Real quick, one more. What if I tell you that it's a right-hand area of 0.12? Which z-score, so for which value down here, gives me a right-hand area of 0.12? Now, particularly those of you that don't have the left, center, right, okay? If this side is 0.12, what's this side? I still can't hear you. 0.88. So you're going to do the inverse norm of 0.88. It only, and frankly, even if your calculator has left, center, right, where this is going to, there are going to be times later on this year where you need to be thinking in terms of left-hand area, okay, where your calculator doesn't have the left, center, right, and you have to use the exact same process. Okay. All right. This is a good, let's just take like a 5-minute breather. Are you right? He's a pretty decent tennis player. No, Rafael Nadal. Okay, so anyway, Rafael Nadal. So, oh, come on. Shouldn't be this hard. All right, there we go. All right, Rafael Nadal has, like when he serves the, you know, they serve and it hopefully is going really fast. If the serve is really fast, it makes it harder to return, yes? Okay, and let's go ahead and say that his average speed at Wimbledon on his first serve is 115 miles per hour. Okay, with a standard deviation of 6 miles per hour. What do you guys think?
Sure.
Sure? Sweet. Okay, so we could draw that picture. That's not a very good one. All right. And where would you like me to, what would you guys like me to put right here? 115? Because that's the average, that's his mean speed. And what is the standard deviation? 6. So the first thing I'm going to tell you is no matter what, if you use the calculator to do normal distribution stuff, anything, if you choose normal CDF, if you choose inverse normal, I expect to see a picture. And on that picture, all of these things need to be there. Normal curve, center, and spread. Has to be communicated to me. Everybody good so far? Okay. Now, the question is asking what proportion or what is the probability that his speed on a given serve is bigger than 120 miles per hour. So I could write that 120. Notice that I'm kind of trying to make it like close to like, since 120 is a little bit under 1 standard deviation above. Is everybody good? All right. So this, from here, I'm about to take you guys kind of like on a spiraled walk to do this question, and then we're going to spiral back to an easy part. An easier way to do it, okay? Everybody okay? Is this serve, the 120, is it fast?
Yes.
Super fast?
It's pretty fast.
Pretty fast, but compared to, relative to, I think he goes by Rafa or Rafi, is like what his fans call him, okay? And relative to his ability, is this like one of his best?
No. Probably
Not one of his best, but
It's
pretty good.
average.
How could you describe where it is? Above average? More specific?
Slightly above average.
Couldn't we find his Z-score?
Yeah, we can.
Sophia, I'll broadcast the calculator when we get to that part too. So what is the Z-score? How do we find it? We would do 120, the actual value that we're looking at, minus the mean, divided by the standard deviation. And that'll tell us how far above the mean he actually did. 0.833, I hope, yeah? Oh, yeah. Do you want me to go yell?
Yes.
Who is it?
I don't know, but they're loud.
It's pre-kill.
Is it pre-calc or is it like, if it's freshmen, I'm not going to yell because they're already terrified of me.
It's sophomores.
Oh. Yeah, shoot, I think it's coming from Lombardi's classroom.
Yeah.
Go yell at Mr.
Go
I
yell.
think it's inside Lombardi's classroom.
Mr. Martis.
Max,
You guys, I'm not going to be able to keep a straight face.
when I walked past you guys watching film at lunch yesterday.
Oh. Oh, I love.
Did Jack practice that a lot? Jack, check this one out. I have a picture of you. Dude, Jack, look at this one.
You probably participated.
You will do it again if you want to.
Yeah, you got it.
Max, 22 versus. Probably like
I just did I say it right? Did I?
Yeah, I think that's how I got it.
You got laughed.
Our seventh period class was my eighth period class. I saw them couldn't yell. Lombardi's seventh period class is almost all that go from her room to my room.
I'm sorry. I'm never doing really bad.
Okay. Z is great. So we got the Z-score to be 0.833. And I'm going to do this. And do this for now. All right. Now, if I draw this picture, this would be, and this is all those Z-scores, yeah? And Z-scores have a mean of 0 and a standard deviation of 1. 0.833 is at the exact same place, relatively, and if I shade that to the right, I'm going to get the, do you see how those two graphs If you take the scales away, look identical. Okay, so when I find the area to the right here, using that standard normal curve in my calculator, go to that second vars and choosing normal CDF and 0.833333 and a gajillion. I get 0.202. Everybody good? Now, I could just as easily do this graph. And if I do it on this graph, what's my lower boundary? What's the lower boundary of what's being shaded here? 120. What's my upper boundary? A gajillion. The same big number that I already had in there, yeah? But now I have a different mean. So when I fill, oh, you guys can't see this. My bad, y'all. So now when I fill up, oh boy. Can you see that?
Yeah.
There we go. Now when I put in, the number I'm going to put in for my mean here, if I'm doing it from this picture, is 115. And for my standard deviation, 6. Is everybody good? And I get pretty darn close to the same answer, yeah? Because the 0.833 was rounded. Notice when I typed it in, I used a lot more than 2 threes, and because of that. If I had put 5/6 in, because that was the decimal that we did, that's what it would have worked out to be. So either way, my answer is that the area is 0.202, okay? And what that means is 20% of the time, Nadal's going to surf faster than 120 miles per hour. That's what that tells us. It's pretty good. All right. So if I ask you guys, what percent of the time will he surf between 100 and 110? Well, let's look at it. My normal curve game has definitely diminished over the summer. So you need to, when you do this, draw the curve, label the mean, label the standard deviation. And if you have a normal curve that doesn't have any shading on it, you'll be irritated with me. It needs to be shaded. Not just the boundary marked, but you need to shade one side or the other of any given boundary. All right. What do you guys think here? What should we do? We don't need to. We can plug it in just like it is right now. Now, can you find the z-score? Sure can. And is it important to understand the relationship between the red graph and the black graph and how they're the same graph, just kind of one is standardized? Yes. And we'll have an example in a little bit that gets to the why we need to understand that. Okay? But if your calculator can do it as is, I'm fine with you just doing it as is. I don't know what the answer is, though. I do, because you guys are the 4th time I've done this problem. You got 0.196? Feeling good? All right. How about this one? According to the CDC, The heights of 3-year-old females are approximately normally distributed with a mean of 94.5 centimeters and a standard deviation of 4 centimeters. What is the 80th percentile? What do you guys think? What should I put in the center? 94.5? Okay. Anything else you want me to write down? The standard deviation being 4. Cool. I'm going to pretend I don't know anything, so if you guys want to tell me anything else I should do. Go ahead. Okay.
Because of like what we did on the other one, could you put like an X or something and then
Okay, so tell me, where do you think that X should be?
like to the right of 94.5?
Like right about here?
Yeah, where it
That's right. And then I'm going to do this, right? That's going to be a boundary. And then I said every normal curve you'll ever give me will be shaded. Where should I shade it?
to the right.
To the left, actually. To the left, because it's 80% higher.
To the right.
Percentiles are the percent that are less than. They're always less than. So to the left. Everything you own in a box to the left. Just remember, okay, percentiles, go with Beyonce. Everything you own in a box to the left. And I'm going to go ahead and label that area as 0.8. Now what? Now we have all the hard work done. We just put it in the calculator. Now, as you put things in the calculator, guys, if you notice that you're putting something in that you haven't written down yet, that's your hint that you need to write more down. If you have to tell it to the calculator, you have to tell it to me. When we choose inverse norm, have we told me inverse norm in some capacity? Sure. Because we have a normal curve with an area labeled. It asks you for an area. We put in that 0.8. We put in the mean. We put in the standard deviation. 97.9. Is that what it is? 97.9 centimeters. Inverse norm.
Explain that again, how we should put this in.
That's fine, you put 2.
Can you see my calculator? Do I need to make it bigger?
Make it a little bit bigger.
Yeah.
There we go.
All right. So according to this picture, which now is there we go. All right. So you're going to go into that inverse norm. And the reason I know I'm doing inverse norm is what I know right now is the area. And in that, I'm going to put 0.8. But instead of using 0 and 1, what is the mean of my graph? It's 94.5. So my mu is going to be that 94.5. And then the sigma is going to be 4. Ellie, is this answering your question?
Yeah.
You feeling okay? All right. Now we can talk about the cicadas. This was way funnier a couple of years ago when it was like all the cicadas were out. The lengths of cicadas are normally distributed with a mean of 3.1. And we find out that a cicada has a length that is 2.8 is the 43rd percentile. So that area to the left of it is 4.43. Can I use normal CDF? Because I have the boundary, right?
No.
Why
it's
not?
the standard deviation.
Because I don't know the standard deviation. Can I use inverse norm? No, because I don't know the standard deviation. Is everybody with me?
Yeah.
So for right now, I'm just going to put question mark. Now, we do have a formula that relates data points to the mean and the standard deviation. It is that z-score formula. The z-score formula looks like this. Z equals x minus the mean divided by the standard deviation. And right now, we have two of those values. The x is 2.8. The mean is 3.1. Is everybody good? And that one other piece of information we have is the 43rd percentile. Is this okay? So what we're going to do is we know something about z-scores. Don't we know the mean and the standard deviation when we're dealing with z-scores? What was the mean of all the z-scores? Not the standard deviation, the mean. 0. And the standard deviation was 1. So if I can find the z-score for the 43rd percentile, by using inverse norm, right? Now, I bet I can guess. Do you think I can get close? It's negative, but barely. Like negative 0.23. How close am I? 0.17? It's negative 0.17? Okay, so I get that from this that the z-score is negative 0.17. And that's just using inverse norm, okay? Then I could say, well, what is that standard deviation for this to be true? I don't know the answer. I'm sorry?
1.7.
Is that what it works out to be? 1.7?
Yeah, that's 6, right?
It'll be close. If you rounded here differently, you would get a slightly different, and I'm smart enough to figure that part out. Cool. We are not going to assess normality today. We're going to do that after the quiz on Friday because you guys, there's enough on this to last a lifetime. Okay, so you guys can work on the review for a little bit.